Hello everyone. Today we're going to talk about reaction mechanisms and rate laws. Now, reactions rarely happen all at once. They usually take a few steps, and this series of steps is known as the reaction mechanism. That's the series you see below. Now, reaction mechanisms usually have a couple fast steps, or one fast step, and a slow step. And the slow step is what determines the overall reaction speed. The reaction is not going to move any faster than what the slow step allows. Now, when you're making your rate laws, you make your predictions based off of the slow step and anything above it. Here, we don't have anything above the slow step, so we just focus on this guy. We don't really care about this one at the moment. Now, for the slow step, you look at the reactants, these guys. And to write your predicted rate law off of the reaction mechanism, you're going to set it to rate is equal to K. K is our constant, which is always there, times NO2 to the power of 1, since there's a 1 coefficient out in front that's implied, times NO2 to the power of 1. Now, since we have two NO2s, mathematically, that's kind of the same as having the same base, so you can just add the exponents since you're multiplying them together. So that is the same as saying rate is equal to K times NO2 squared. And that is our predicted rate law. Predicted rate law. Now, we make predicted rate laws so we can compare them against reality. The information, the data you see down here, is experimental data. This reflects reality. The predicted rate laws only is what we think might happen. What we think. And the reason we compare the two is to see if our rate law reflects what happened with what we think with the mechanism. We can't really see a lot of chemistry down on like the molecular or the atomic level, so we kind of have to make predictions and see how well we can predict things. In the end, reality always wins. So if reality does not match what we think, it means what we thought was wrong. So we need to change. So here, this is the same solving you've been doing for the past couple of weeks. You need to solve for x, and you need to solve for y. For x, you need to find two experiments where the concentrations for y are the same, because we're going to have to end up canceling out y. So let's choose experiments 2 and experiment 1. And I recommend putting the larger numbers on top to make the math a little bit nicer, but it's ultimately your preference. Now the rate for experiment 2 is 1.4 times 10 to the negative 7 molarity per hour equals K, our constant, times the concentration of NO2, which is 0.76, times 10 to the power of negative 4, times the concentration of CO, which is 5.1 times 10 to the negative 4. Right, that right there is experiment 2. Now we're going to put a similar thing on the bottom with experiment 1. The rate for experiment 1 is 3.5 times 10 to the negative 8 molarity per hour. We have our constant K. Now it's going to be times, or the concentration of experiment 1 for NO2, which is 0.38 times 10 to the negative 4 times the concentration of CO, 5.1 times 10 to the negative 4. Now the NO2s are to the power of x, the COs are to the power of y. Now the K's are the same, so we can cancel those out. Anything divided by itself is 1. Here, the concentrations are the same for CO, so we can cancel these out, leaving us the reaction rate and the concentrations for NO2. Now if you divide these two together, you'll end up with 2 to the power of x. Here, if you get out your calculator and calculate 1.4 times 10 to the negative 7 divided by 3.5 times 10 to the negative 8, you should get 4. Now you might be able to eyeball this and see that x is 2. If you end up with some weird number, there's an easier way to do this on your calculator. Take the natural log of both sides. And it's important that you do this to both sides. If you only do it to one side, your equation has changed and it's no longer valid. Now when you take the natural log of something and you have x to the power or 2 to the power of something on the inside or anything to a power, you can actually pull that exponent out. So this is the same as saying ln of 4 equals x times ln of 2. These two guys are equivalent statements. Now if we divide both sides by ln of 2, we can isolate x. So ln of 4 divided by ln of 2 gives us is equal to x, and x is equal to 2. So our experimental data has said that x equals 2. Now when you're doing this on a quiz or an exam, I recommend going up and writing that out next to your data, because it can get messy on your sheet and this just keeps things organized. Now let's take a second, erase what we've done, and try again for CO. Now when you do this, you're going to see something interesting. And if you can recognize this pattern beforehand, it will save you time and math on a quiz or exam. Take a second to erase this. I recommend you pause the video and try solving it for yourself. So here we need 2 experiments where NO2 is the same but CO is different. That would be experiments 3 and experiment 1. And again, I recommend putting the bigger one on top. Here for experiment 3, you have the rate of 3.5 times 10 to the negative 8 equals K times our concentration of NO2, which is 0.38 times 10 to the negative 4. That's going to be to the power of x times the concentration of CO, which is 8.6 times 10 to the power of negative 4. All of that to the power of y. That is experiment 3. You're going to do the same thing on the bottom for experiment 1. So the rate is 3.5 times 10 to the negative 8 equals K times our concentration of NO2, which is 0.38 times 10 to the negative 4, all to the power of x, times 5.1 times 10 to the negative 4, which is our concentration of CO, the power of y. Now I want you to take a second to stop and look at this. The concentrations of CO have changed. These two are clearly different. But take a look at the reaction rates. They're identical. They haven't changed. We have changed the concentration of something, but had 0 impact on the rate. That tells you it is not involved in the rate law. So, when that happens, whatever is inside is going to be raised to the power of 0. And anything raised to the power of 0 is equal to 1. Now let's try writing our experimentally derived rate law. What has reality told us? Here, rate is going to be equal to K. K is our constant. We said that this guy isn't involved and is essentially equal to 1. You multiply anything by 1, it's just going to be itself, so we can omit this guy. So it's going to be rate equals K times NO2, and we said here that X is equal to 2. Rate is equal to rate is equal to K times NO2 to the power of 2. This is experimental. Let's compare that to what we predicted. What did we think was going to happen? Here we predicted the same thing. Rate equals K times NO2 to the power of 2. Our prediction was correct. So this helps to confirm that our predicted reaction mechanism is correct. I hope you found this video helpful, and I'll see you in class tomorrow.